Chromebooks up and going. I should have, this is my wrong paper. I actually should have talked about the answer to this within the last few days as we were talking about the space unit. Let me get these remote kiddios. I got Scholar. I got Josh.
I heard these two students in the hallway trying to talk about how the Big Bang theory was solved. Like the Big Bang was solved by human eye. I was like,
you can't, like, not with our technology now. We can't.
You easily can't, but
You can't. There's nothing to look at. Like, there's nothing there. Like,
I don't know. They just heard the hallway. Yeah, the Big Bang can be seen by the human eye. I was like,
no, it can't. There was no matter. Well, see, I mean, maybe. I don't know. Let's see who else is in. I got Cole. I got Kaylee. Okay, I got all of them. And honestly, I don't know how many of my classes I really did go into the answer behind this. Some of my students knew the answer to it, or they knew what it was about. They just didn't know how to answer it properly. So we are talking about telescopes today, talking about some of them specifically because of their importance. I'm not going to talk about every telescope that's ever been made, and I'm not going to talk about every type of telescope that you have.
I'm guessing we're talking about the east.
Well, there are examples that I have. That is frozen. And so these obviously work from Earth. Now this one's in real bad shape. It's missing its finder here. I have another one that's like it back there, and that's even worse shape. It doesn't even have an optic lens. So I told them, I said, yeah, don't throw them away. Maybe I can find replacement parts, but it's probably not worth it because the lens in this is filthy. But these work from Earth, yes.
I have a telescope at my house, and I tried to set it up. Could I bring it up here?
Yeah. What type is it?
Can you help me set it up?
What type is it?
It looks like that.
It swivels like this?
No. It's not as big as that. It's definitely a smaller model. But it does swivel like that, and it has that lens, like the eyepiece right there.
Does it have a counterweight on it? Is it Newtonian? Because I hate those.
I don't know.
You know what? When we go through pictures, if you see one that looks like it.
I would imagine it's pretty simplified. Like, it's called like a star navigator. It's by MEAD.
Mead. Okay, Mead.
Yes.
Celestron is the other major company that makes telescopes.
Okay.
Used to be, Polaris used to be popular too, but, huh? Yeah, that's mine. Mine is a Celestron, so that one's mine from home. But anyways, so these guys do work from Earth. Certain telescopes work from Earth, and they also work in space. But these three types, they don't work here. Why do we have to put them in space to let them work? Because they do what? It's not gravity. It's the atmosphere. That pesky atmosphere does a really good job at blocking these and most of this from our sun. Obviously, some ultraviolet gets through because we get sunburnt, right? Some of us, like me, I don't tan, I burn. Like, I have to have multiple burns to obtain even the smallest tan. Like, it's horrible. Horrible. But that means that we also can't see these using those scopes from Earth because it doesn't have the ability to penetrate through the atmosphere, either from the sun side in or from the Earth side out. But the other parts of the spectrum, visible light, which is how these operate, both of these are well, this is a Dobsonian and that's a Cassegrain, but they still use visible light. We use radio scopes. We listen to radio transmissions. That's how the radio works. It's how television signals, like if you've got DirecTV or Dish, it bounces the signal through our atmosphere to the telescopes and back again. That's how microwaves do that. Infrared can do that. Okay, but these parts of the spectrum, yes, some UV can get through, but the other ones don't. So they don't work from here because of that pesky thing called the atmosphere that allows us to live. Fifth period has an extra 20 minutes, and like everybody finished a little 10-question assessment that goes along with it. Now the first thing, oh, did anybody want a paper copy of the notes? Okay, I'm so sorry, they're up here. So I know some of you like to write. And you're more than welcome. You're more than welcome to upload images to supplement your notes, especially Hubble images.
Oh, okay. Oh, the notes are already on there. You can write them down.
Paper.
Oh,
Maybe I'll put paper.
the notes are great.
Yeah, well, they end up being test grade at the end of the 6 weeks. I'm checking what are you doing digitally, or are you doing on paper? Because I know some of you learn better by writing on paper. Don't really learn by writing on computer.
I'm gonna look on the, I bet you.
At the end of every lesson.
I bet you can.
go back to it.
I'll be here.
It's like a little pen question.
How you gonna look like if I'm not?
Is that okay?
You know what?
Okay, so. Yes, if you are missing something in Canvas, you have through tomorrow to get it fixed, because I'm going to put a hard block on things. You do have 2 attempts at these little quiz assessments at the end of everything. If you make like a 20 on it, I highly suggest going back and redoing it. But you can't do it more than twice. Now you have a couple of things that are at the top of this that aren't really expressed out. I just went straight into the types of scopes, but these are all visible light. They are optical, and that's visible light from our eyeballs. And what all 3 of these do is they magnify the objects. And that's one thing that all visible light scopes do. But they also gather much larger amounts of light than what your eyeball can. It focuses it. Now they do it different ways, but it amplifies the visible light that's present to increase the image. Reflecting telescopes. Well, we've had actually both of these for a while. They just weren't engineered to look at the night sky. They were looked to look across the land for surveying things, or like, pirates with their spy glasses. That's how they were used. And the refracting one was actually developed first by Galileo, but I'm going to talk about the one with mirrors first. Isaac Newton invented the modern reflecting scope in 1668, shortly after the law of gravity and gravitational motion. And reflecting telescopes use mirrors. They had Dobsonian, which is this big guy. I got to take my lanyard off because I almost choked myself this morning. There you go. If I take them off, it's heavy. You can see I'm here in the back, and this thing's actually filthy. I don't know where they put the lens cap for this, but it has to actually be disassembled and cleaned, let alone the fact it's missing a bunch of stuff. Put it back into its harness. So the light comes through here. Obviously, it would come from the sky, but the light comes through here, bounces off this back mirror, this main mirror, which then focuses it onto the mirror that's on the other side of this. It's this little thing. Next shoots it up through the eyeglass, through the lens, and we can put different lenses. This is a 9mm lens. And then you can see things. Now, the bad thing about a Dobsonian is you have to manually move these to track across the sky. If you have a telescope, it is probably one of these 2. Refracting ones use lenses, and that one was invented by Galileo. Remember, he did not invent the first telescope. Galileo was the first one to use them to look at the night sky, but he did invent the modern version of a refracting one, which uses a lens. Now, if you have a scope and you know how to use it, even if you don't know how to use it, you use it. It's inverted. Okay, it's not like binoculars or like the scope on a rifle. Okay, with those, up is up and down is down and left is left and right is right. With most telescopes, it is an inversion of the image. And so when it looks like you need to move something, the scope to the right, you really need to move it to the left. And if it looks like you need to move the scope up, you really need to move the scope down. It takes a little getting used to if you have one that you have to move by hand. I used to have a bunch of Newtonians. They take forever to calibrate. You have to calibrate them to the North Star Polaris. You have to know your latitude. You have to set the azimuth and all that good stuff. And then after about an hour and a half of calibrating this thing, then you can use it. And the thing that's nice with a Newtonian is it follows, once it's set up, all you have to do is turn the little handles and it will track with the star. That's how they work. They have big counterweights. Is yours like that? Okay, when you have a Newtonian, they are a royal pain in the butt to set up. But if you do successfully set it to Polaris, that's the hard part. And we had a hard time when I ran an astronomy club because they're cheaper. I bought a bunch of them. I was like, man, it'd be cool if they learned how to use these. And they hated them because it takes forever to set them up. And by the time we set it up, it was time to leave because it was school the next day. And I had a 7-year-old with me at the time. And yeah, that was fun. A multiple mirror scope will take a combination. And the one that I'm going to show you, there's 9 different lenses that are in it. And they give you a better image. The more ways you have to see in a scope, they don't have to all be visible, but the more ways you have to see, the better the picture is. Now mine, I had a little guy, and he was a lot easier to calibrate. But this guy, if it is calibrated, I can tell it in here. I want you to look at this. And he'll go, okay. And then it will track it across the sky. Then I've got cameras and all different kinds of stuff where I can stack images. And I haven't taken it to go see how close wrong planet, Mars is, but I know when Mars was close, I can see the ice caps on it with this guy. Can see the spot of Jupiter and the different color bands. I can see the rings of Saturn. It's not quite powerful enough to see the Cassini line, that like dark gap that's in the rings of Saturn. Don't know what that is. That's what that is. I don't know where I put my clicker. But this guy is also sort of a pain. You have to have stars that you know by name. I wonder what I did with the clicker. Oh, there it is. And then it'll do its thing. That one was about $1,500 when I bought it. That was a while ago. You can get a 4SE, which is this thing's little brother, for about $400. But you have to have batteries because you're out in the middle of the field. It's not like you can plug it into the dirt. And you have to get lenses. With this one, when I look at the moon, if you just look at the moon with it, you'll go blind. It's that bright. So you have to put, come on, you have to put a lunar filter on it. And if you ask my kid the color of the moon, she's going to tell you it's green because that's the shade that this turns it into. But if you do look at the moon with one of these, with a Cassegrain like this, without a lunar filter, yeah, have fun seeing. But certain planets, certain nebulae, would use a different filter. They're just different colors. It just lets you see things better. So if you do end up getting one of these, it's sort of worth it to get a better one where you can actually screw the lenses inside this. And then this would pop down. This would pop down in here. So, I don't know. It's in this area, there's enough light pollution that I don't know very many people that have their own personal telescopes. I just don't. I've had telescopes ever since I was like 6. These are old school. They come in all different sizes. You can get them rather inexpensively. This is probably the type that you have. Okay, this is a Newtonian. Same concept. This one is sort of like this guy, but it has these counterweights. So you've got these little handles that you turn. So once you set the azimuth and then you get the right latitude, which I don't know the latitude here. It used to be 30 degrees, like right at 30 degrees where I moved from. All you have to do is use these if it's set up right, and it will follow it for you. So you're not having to like manually move it. But until you get it set to the North Star, you'd have to manually swing these things around. Well, where's my cursor? There it is. All right, the Palomar. This guy is monstrous. It's been around for a long time. Hubble was the first person to use this. This thing discovered quasars. It was the largest telescope for like almost 50 years, till about the 70s, give or take. Observatories, okay, they're normally in the desert. Okay, like McDonald Observatory, that's out by El Paso. Or they're on the top of a mountain, like the one that's on top of Hawaii, the little Hawaiian island. The reason why they do that is because, well, first of all, it's in the middle of nowhere, so you have no light pollution, but it's cooler and it's drier, and that actually calms down the atmosphere. You know, it's hot and gross and humid in Texas. That actually makes the atmosphere shimmer, and it makes everything look like it's sort of wobbling. So what's best for looking at the stars is out in the middle of nowhere, if you can do it, on cooler nights that are dry. But like I said, good luck doing that in Texas. This guy's got 1, 2, 3, 4, 5, 6, 7 different lenses in it. You don't need to know this one specifically, but this is an example of a multi-mirror. I don't know where Mount Hopkins is, but it's apparently in Arizona. Radio telescopes. These are the biggest of the big. They can be like 1,000 feet wide. They're huge. They detect radio waves, which is why they're called radio telescopes. They get really inventive with their names on these. The biggest one that I know of, and I don't think it's been surpassed, I'll show you a picture of it. It's in the forest of Puerto Rico. It's suspended by cables. It's so big. I mean, they're not going to let you drive around on it, but it's so big that you could literally drive around it in your car. You destroy the equipment, but you could. SETI uses these out in the desert. They're listening for radio transmissions from extraterrestrial life. Yes, they've heard weird things. Those aren't as big. One thing that radioscopes all have in common is the surface that the signal bounces off of and then focuses up to the actual antenna. That surface is almost popped like a golf ball. Like you see all these little facets all over it, and that's to actually angle that radio wave, focus it into a point, and it'll actually hit the receiver, the actual antenna. Infrared scopes, these are the ones that see the farthest back in time. Infrared goes much further back in time. It's a heat signature. We sort of talked about that when we introduced the Big Bang. The hot part of the Big Bang, the part where there was actually matter present. Because like you said, you can't see before that because there's nothing to look at. There's nothing to see. The only thing that they can think of is to use something like LIGO and try to listen to disturbances in space-time, gravitational waves, which we are just starting to do. We're at the early stages of that, but I don't think we have anything like that up in space yet. I know we do down here on Earth. Probably in the future, I hope in my lifetime, because I love this stuff. I love learning about this kind of stuff. The one that we're going to put up in just over a year, James Webb, it's going to look at the very, very, very early formation of galaxies. It should be able to appear much further back in time. It's going to take it 6 months to go where it's supposed to go, and then it's going to assemble itself like a transformer. Pretty much. Observatories, they can be on Earth. They can be in space. They can be traveling through space, or they could be in orbit looking at something specific. We can tell them to move to other places. They have some type of a scope on them. They can have multiple types. The ones that we launched in 77, the 2 Voyagers, they are the furthest out, about 150 AUs. I'd have to cheat and look at NASA's site, see exactly where they are because they're moving. If we need to send them a signal, or if they're sending a signal back to us, it takes about 40 hours one way to reach us. So they're quite a ways out. Okay, so this is the telescope I was talking about, the one that's suspended in the jungle. This is 1,000 feet from one side to the other. It's absolutely massive. The guy off to the right's a little bit smaller. It's still big, but it's not as big as this one. And like I said, the one that SETI has dozens and dozens and dozens of them out in the desert. They're probably about the height of this room from here to here. Like I said, their surface is dimpled like a golf ball. They all have that same faceted this part. So the way that they work, once again, the radio wave comes in here and it bounces off all of those facets and it's focused. This is actually the antenna that receives the signal. The dish just focuses that to that antenna. That's how all satellites work. Like I have a direct TV dish on my house. Not as big as this. It's what, like that big? Okay, so it hits it, and then there's an antenna in the front. And that's how the signal gets in my house. Just have to hope it doesn't rain really hard, or I have new TV. All right, so this is a Schmidt. In general, Schmidt scopes are going to combine a mirror and a lens, so they see better. This is a stellar nebula. It's not a planetary nebula. And even though I don't know what name this one is, because I don't know if the name of it is UKS1 or if that's actually the name of the scope that took this picture. The reason why I know it's a stellar is because of all of these blue stars. Are those old stars or new stars? New stars. Blue means young and red means old. And yes, you can have different colors in the same system, but if it is primarily blue, then you have a younger one. That's how we know that our galaxy is not in good condition, is we have way more red than what we should, which means that our galaxy is dying. There are some regions that are still birthing stars, but there's not very many. Poor Milky Way. All right. Hubble. If you've ever seen, you mean go back?
No.
Well, I mean, ultimately it could be destroyed or it could blink out, but I mean, if it has a whole bunch of red, it's not going to be lasting much longer. And if we're looking at galaxies, who knows how many light years away, who's to say that the things that we see are not already gone? Because it takes time to reach us. If you have seen the movie Gravity, which had so many things that were not even remotely physically correct, yes. But it started off where they were at Hubble and they were doing some kind of maintenance on it. Hubble to me has always looked like a giant trash can. It just has. It's not a trash can. It was put up in 90. I was in middle school. I remember this as a child. And NASA put it together and set it all to go and set it up into space. And they got the first transmissions back and they went, oh, I can't say that word, especially since I'm recording myself, because all the images were blurry. No, I don't want to say bad words. No.
What if I said first?
No, don't, because we're live streaming and you'll get in trouble. No. I'm sure they said lots of bad words, to be honest with you. Where are you at? You're Jillian. Are you leaving? Yes. Okay. I will upload this as soon as I can. Okay, so they had to just send a cosmonaut up, astronaut, whatever you want to call them, and they had to just calibrate it, and then all the pictures were clear. It is still in use. Okay, they're updating its technology. The reason why I probably will never stop talking about Hubble, even if we decide to decommission it. This was the first one that looked deep into space. This is the first one that gave us all these beautiful images of the nebula. This is called the Pillars of Creation. That is the name of this Magellanic Cloud. And you see stars, you see blue and red, and you see all these sections of cosmic dust. I don't even remotely have enough time to upload a bunch of images, but if you want to Google Hubble images, they're absolutely gorgeous. This is called the Horsehead Nebula. Can you see the horse's head? Once I show it, you won't unsee it.
I see it.
Wait, don't.
Yes, it looks sort of like a horse from hell, okay? But here's the eye. Here's the nose. Here's the nostril. Here's the mouth. Here's the chin. Here's the ear. And here's the mane. That is why it's called the Horsehead Nebula, because that's what it looked like.
Wow, I really can't unsee that.
You can't unsee it now. Now, this is called the Cat's Eye Nebula. I honestly think it looks more like a flower, but it's called the Cat's Eye Nebula. It's just its name. I used to have the Ant Nebula, the large Ant Nebula. You can see the head and the torso, and you can see legs sticking out the side. I just didn't upload that image. There's tons of them. Crab Nebula. It's just tons and tons and tons of them. This is the one originally was supposed to go up in 2016. Yes, sir. Sure. Okay, so this James Webb is named after an important physicist. Well, yeah, I guess you call him an astrophysicist. It's been pushed back to Halloween of next year. Once it goes up, it's going to take it 6 months to get where it needs to be. It's going to go to a nice quiet space out in space. And it's going to transform itself from its movement shape to this. Now, to put this in perspective, these are 3 hexagonal panels. There's like 10, 11, 12, 13, 14. There's at least 30 panels on there. Each golden panel is taller than I am. So it's an absolutely massive, massive thing. It will be using infrared. Do you need to see my blue folder?
Is that blue one?
I do. The question is, where did I put it? Here it is. Does it need to be updated?
I need to change some stuff.
Sure thing. No problem. It does see an infrared. So an infrared is the ability to see further back in time. Is it going to be able to see the beginning of the Big Bang? No, because we can't see that, but it will look at the very early formation of galaxies. And there's a really good chance that our observable universe is going to become larger than 13.8 billion years. I have seen a few numbers that are larger. Huh? Anything that you look at is using stuff from the past. Even technically, you looking at me, you are seeing then, you are not seeing now.
Oh.
You sure?
It's true. It's well, I told fifth period how we could do time travel, and that really freaked them out. But we have extra time, and we have extra time in fifth period. We have like an extra 10 or 15 minutes. If we have time, I'll explain it. I've got the piece of paper right there.
You have like 4 more notes.
Are you ready?
Yes.
Yes. Rapid fire. Spectroscopes. This is the one from over 100 years ago. This is called a spectroscope. It uses a prism, opens up the rainbow, Roy G. Biv, and it uses that to take a look at the chemical signatures that are present in stars, and yes, planets too. This one looked at stars, not planets. Kepler, which was a spectroscope, was looking at the chemical signature on other planets to see if they had the possibility to harbor life. But it uses the same thing. Certain elements and certain compounds will show different colors of our spectrum. That's how they know what elements are present in which stars. You don't need to know the people, but Maunder is this guy. This is how you look into it. Looks here, and it like stuff comes in, and then it bounces it this way. There's a mirror here. There's a mirror here. But that is how we do that. They don't just say, "Oh, I think that one's got helium in it." The EM spectrum. And you actually gave you a colored EM spectrum in your notes in Canvas. We only see this with the naked eye, 7%. That's visible light. Now, there are animals, specifically bees and butterflies, specifically, that see in ultraviolet and in light, so that flowers look different to them. A white flower to us might be bright pink to them, because ultraviolet's different, a different part of the spectrum. There are animals that use visible light and infrared. Boa constrictors can see your heat signature. That's infrared. We can't see an infrared. Now, we can put on special glasses. You've ever seen the movie The Predator? Okay, like that. Cops do it. Cops do it. They have night vision, and then they've got infrared, and so they can see the person running away from them and trying to hide because they see their heat signature. They glow. Yes. You cannot hide from that. Didn't they stop that TV show? I think they did. I always love people that get bit by dogs and they get tasered. I don't know why. I do. I'm like, go dog. You need to invent like a taser jaw for a dog, and that would just be even better.
I know they get tased.
Bit.
Well, the dog gets tased too. So.
But anyways, so the worst are gamma. These are the smallest waves, which have the highest frequency, which is why they're more dangerous. Remember these? And some UV, the sun blocks this, but it lets everything down here out and through. You ready for the next one? Because the next one's the one that you have. You have this one. I gave it to you. Because I didn't want you to have to draw it and write all the numbers on it. So this is infrared heat. This is microwaves. That's how Doppler works. Like when I was watching that hurricane going straight towards my house, it sends a microwave out, and depending on how quickly it bounces back, it tells not only how far away the rain is, but how dense the rain is, and it changes that into a color image for us. Similar to sonar. So like the animal makes the ping noise, or the submarine makes the ping noise, and it listens to the echo, and it says how far away things are. People can echolocate. Blind people can see, if you've ever seen those. They click, and they listen to how quickly the click comes back, and it superimposes an image in their brain. And then we've got, these are all radio waves. The two different like radio stations, the type that we use for televisions. And then these are like the old school radios, like emergency things. All right, Doppler. I have something. Oh, you know what? I wonder. Good. Sometimes I forget to mute that, and then they get that real bad echo. I can show you Doppler effects. Let's do the little one. So the pitch of this is not going to change.
Well, that's tricky.
So this thing makes a noise. Okay, you don't hit it on stuff. It's not like a shooting point. Yes, that was very odd. Yes, it is. Okay, so this is its pitch. Okay, I can make it a lot louder.
Do it. Oh my God.
But do you hear?
That's insane.
Do you hear how it's sort of changing as it comes towards and away?
You can do that to tears too.
Yes, you can. Yes, you can. You just got to find its natural frequency. Sorry, people online. That is loud. So, as it's coming towards you, the sound waves are compacting, and it makes it sound like the pitch goes up. The pitch does not change. It sounds like it does, but it doesn't. And as it goes away from you, these waves are spreading out, and it sounds like the pitch goes down. So car horns, train horns, police sirens, as they come towards you, yes, obviously they're getting louder, but it does sound like the pitch goes up.
Can we try that out?
I guess when we're done, we have time. And as it goes away, it goes down. Does not really change. Now, that is similar to what is called, the last one that we have, parallax. But parallax isn't the audible version, it's a visual version. when we look at the stars at night, we are all moving together. Takes 200 million years to go all the way around once, but we are moving as a unit. Because we are going around our sun, the position of a star will look like it's in a different place at different times of the year. It's really not. It's the fact that our position has changed in our orbit that makes it look a little different. It's the same concept as Doppler, it's just not sound. And I have nice, loud, annoying examples to be able to do Doppler with you. I have so many physics toys. I miss teaching physics.
I need to bring one of those to school.
What? The singing, you can get them pretty cheap. I think I got those 3 for like $20, but they don't work. So I tried to do it with my left hand because I don't have that stuff on it. Like, I mean, I can get it going a little bit, but that's because my fingers are oily. But if I use the rock rosin, now this is a bigger one, so it has a lower pitch.
Oh, you have to use that rock rosin?
It has to cause vibration. So the grab slip, like you can't see it, I can feel it.
Oh, I know.
And then the harder I pull, the more energy that's in it, the louder it becomes because I've increased its amplitude.
That's great. Let me give that a try.
Okay, now we're essentially done with this. Let me stop my recording. There's the little 10-question assignment, essentially the assessment that goes along with this. It does say quiz. Go back and make sure that you're not missing them because, like I said, I am putting a hard freeze on stuff tomorrow. Stop recording. What's it under? Hold on, I'll show you. Stop recording.